Welcome to The Explainer. Today, we're going to break down the core principles of reinforced concrete design. We're talking about the fundamental philosophies that make sure our buildings, our bridges, everything we rely on are both incredibly safe and, actually affordable to build.
So let's just jump right in with the big question, the one that every single structural engineer has to answer. How in the world do you balance the absolute, non-negotiable need for safety with the hard reality of a budget? It's a really high-stakes tightrope walk.
You see, the whole challenge really boils down to one word: uncertainty. The concrete you pour on Monday isn't going to have the exact same strength as the batch you pour on Tuesday, and you can't possibly know exactly how many people will be in a building or how hard the wind will blow 50 years from now. So you need a system, a philosophy, to design for all of these unknowns.
So here's our game plan. First, we'll dig into that core problem. Then we'll walk through the three big design philosophies that evolved over time: the working stress method, the ultimate load method, and the modern limit state method. We'll put them head to head and wrap up with the big lesson.
All right, let's get into it. This core problem of balancing safety, cost, and a whole lot of unpredictability.
So, the very first major attempt to solve this was a method that put safety above absolutely everything else, maybe a little too much so. It's called the working stress method, or WSM for short.
The idea behind WSM was actually pretty straightforward. It assumes materials behave perfectly, like a perfect rubber band that always snaps back. To be extra safe, engineers would then apply a massive factor of safety. This made sure the real-world stresses a building felt would never, ever get close to the material's actual breaking point.
And this analogy just hits the nail on the head. It's like having this incredible supercar that can easily do 200, but you're only ever allowed to drive it at 30. Sure, you're safe, but you are wasting almost all of the car's potential. You're paying for all this power that you are literally forbidden from ever using.
So here's the bottom line on WSM. On one hand, yes, it was incredibly safe, and the math was pretty simple. But it was just hugely inefficient. It led to these overbuilt, bulky, and really expensive structures because you were just wasting so much of the material's strength. Plus, it kind of ignored real-world things, like how concrete can crack under load.
So, naturally, engineers looked at this waste and thought, we can do better. This led to the next evolution, a direct response to WSM's inefficiency. It was called the ultimate load method, or ULM.
Now, this method did a complete 180. Instead of keeping stresses super low, ULM focused only on the ultimate strength of the structure, like the absolute point where it would collapse. The safety part came from multiplying the expected loads by load factors, so you are designing the building to handle forces way bigger than it would ever likely face.
But this approach created a massive new blind spot. ULM only asks one question: will it fall down? It never asks, but is it actually usable? This chair analogy is perfect. Imagine a chair that's strong enough to hold a small car, but it's so wobbly and saggy that you can't even sit on it comfortably. Is it strong? Yes. Is it serviceable? Not at all.
So yeah, ULM was a big step forward in making things more economical, but it completely overcorrected. It totally ignored the experience of the people using the building. A floor might be strong enough not to break, but it could sag or vibrate so much that it just feels unsafe, or develop big, ugly cracks over time. Not good.
And all of this whole journey, brings us to the modern, really sophisticated solution that kind of takes the best of both worlds. It's called the limit state method, or LSM.
LSM is built around this incredibly smart idea of a limit state. Now, a limit state isn't just about the building collapsing. No. It's any condition where the structure stops doing its job properly, whether that's breaking, bending too much, cracking, or even just vibrating in a way that makes people uncomfortable.
And this is the real genius of the method. Every single design has to pass two completely different kinds of tests. First, the limit state of collapse. Basically, is it strong enough? And second, the limit state of serviceability. Is it comfortable? Is it durable? Is it actually fit to be used every day?
So how does it pull off this balancing act? Well, instead of one big, blunt factor of safety like in the old days, LSM uses a much more nuanced approach. It's based on probability, and it's called partial safety factors.
I mean, this is so clever. It recognizes that not all uncertainties are the same. Concrete is mixed on site, it's more variable, so it gets a higher safety factor of 1.5. Steel, on the other hand, is made in a factory under controlled conditions, it's more predictable, so its factor is a bit lower, 1.15. And the loads get factored up too. It's a tailored, really intelligent way to handle safety.
The result is this incredibly rational method that finally finds that perfect balance. It's safe, it's economical, and it gives us buildings that are comfortable and built to last. The only real trade-off? The calculations are a little more complex, and it requires a deeper level of understanding from the engineer. A small price to pay, I'd say.
Okay, let's put all three of these side by side. It's time for a direct comparison so you can really see how our thinking on this has evolved.
I mean, this table just makes it crystal clear, doesn't it? WSM was wasteful. ULM ignored comfort. LSM gets it all right. It's based on probability, it uses those smart partial safety factors, it balances cost and safety, and it properly checks for serviceability. It's really no surprise that this is the standard pretty much everywhere today.
So after that whole journey through engineering history, what's the big lesson here? What's the ultimate takeaway?
It's really this simple. The best design is a balanced one. WSM was way too cautious. ULM was too focused on just raw strength. LSM is the smart, sophisticated approach that finally achieves that perfect balance of safety, economy, and comfort. And that is exactly why modern building codes like IS 456 say you have to use it.
And that leaves us with one final thing to think about. LSM is the standard for today for sure, but it won't be the final chapter. As our materials get even smarter and our computers get even better at predicting loads, what do you think the next great leap in design philosophy will be? What comes after balance?